Welcome to another exciting episode of Algorithm Analysis and Design. I'm your host and your professor, Dr. John Baugh. This lecture we're going to be discussing divide and conquer. So what does this mean? So what is divide and conquer? Divide and conquer is a problem-solving strategy. The general process in a divide and conquer strategy is to break a problem into smaller subproblems of the same type, so basically smaller versions of that big problem, solve each subproblem recursively, and combine all the subproblem solutions to solve the original problem. This process is typically a top-down approach. So in this context, top-down refers to the flow of problem solving. You start with the original problem at the top, and then you recursively break it into smaller subproblems until they're simple enough to solve directly. So general structure of a divide and conquer algorithm looks something like this. So you have the t of n equals a times t of the n over b plus f of n. Now let's go over what this means. So this recurrence describes the structure of the divide and conquer algorithm. The a would be number of recursive calls or subproblems. The n over b, which is part of this t here, is the size of each subproblem. And then the f of n is the cost to divide and combine. So this f of n really is the stuff that doesn't involve recursion itself. So by itself, it doesn't tell us the time complexity that comes after solving the recurrence, usually by techniques like recursion trees, the Master Theorem, or expansion and substitution. We'll take a look at a couple of these momentarily. Some notes are that subproblems must be of the same type in order for divide and conquer to work properly. That's what makes it recursive structurally. And divide and conquer is different from other approaches to algorithm design that we'll look at later in the course. For example, greedy, which makes one decision at a time, and dynamic programming, which reuses overlapping subproblems. So divide and conquer is actually pretty much everywhere. We've got examples of it all over the place. Military strategy, split and isolate enemies to defeat them piecemeal. So Napoleon at Austerlitz. Emergency response, assigning teams to different regions after a disaster. Project management, breaking large projects into smaller tasks assigned to teams. Software development, dividing the code base into modules, developing and testing each separately. And Google search, so index different parts of the web across many machines, then merge the results. So all of these are either divide and conquer or very similar to divide and conquer. So we need some mathematical foundations in order to solve recurrences, recurrence relations. So let's look at this. A recurrence or recurrence relation expresses the runtime of an algorithm or of a recursive algorithm in terms of itself. So we've already done some asymptotic analysis on non-recursive algorithms before. We did that previously. But you have to kind of use some special techniques sometimes when recursion's involved because it can get complex and it's not always immediately obvious how you're supposed to tackle those. So these are used to describe algorithms that call themselves on smaller input. A common structure, as I indicated before, is that the t of n is a times t of n over b plus f of n. A, again, is the number of recursive calls or subproblems. N over b is the size of each subproblem. And f of n is the work done outside the recursive calls, such as dividing, combining, merging, things like that. It's important to note that this is not the final answer. It's a model of the algorithm structure. So recursion trees are one solution to deal with the recurrences. They're often good for estimations and building intuition. We break down the recursive calls level by level. Features are that each level of the tree represents calls at a given input size. They help us estimate total work across all levels. The key idea is that the total cost is equal to the sum of the work at each level. So consider this. Let's consider an algorithm that has this time complexity function description. We've got t of n equals 2 times t of n over 2 plus c times n. So the c times n is the non-recursive work, right? It's not making another call recursively. C times n is work at each level. This is like split and merge, for example, for merge sort. C is the work done at each node, and there are n nodes to do it at in this case, so that's why it's C times n. The recursive work is this stuff. So the if we go back here, A was the number of recursive calls, n over B is the size of each subproblem. So that means that the 2 is the number of recursive calls, and then n over 2 is the size of each subproblem. All right, here's an example. So this is what the recurrence tree looks like for this 2t and then 2t of n over 2 plus cn. You've got work at the top node, which is cn, c times n, at this top node, top call, which would be done after it recurses back. Level 1, you've got this problem split into 2. So you've got t of n over 2 and t of n over 2. When you look at both of them, you have c times n over 2. Sorry, 2 of them, right? Because there's 2 nodes, 2 recursive calls that are doing this work. So it's going to be 2 times c of n over 2. The 2's cancel, you end up with cn again. Then you end up with level 2. So this is the original t of n is split into 2 to get t of n over 2, and then subproblem size n over 4. We've got 4 of those, so that ends up also being c of n. If we keep going, you end up at the kth level. So this is where we start talking about an arbitrary level. And if you look at the pattern that we're getting, this ends up being n over the 2 to the level number. Tells you how many subproblems are involved, right? So there are 2 to the k nodes at this level, whatever this level is going to be. And then we, like level 2, we had 2 to the 2, if our k is 2. So 2 to the 2 is 4, which is why we have 4 nodes. And then it would be n over 2 to the k, which is n over 2 to the power 2, which is n over 4, which is why we ended up with that. But as a general solution, it's this. So if there's 2 to the k nodes at a given level, each has size n over 2 to the power k. That means that the work is what? 2 to the k times c of n over 2 to the k, right? Or c times n over 2 to the power k. The 2 to the k and the 2 to the k cancel, and you again end up with c times n. So every single level is c times n. So that process continues until we have leaf nodes. This is where each node is at the t of n over n, right? We've got n nodes at the bottom. That's the typical approach if we use a pure theoretical approach. We'll see that merge sort, we go down to the 1 nodes, and the pure approach, in practice, they might go down to size 7, run insertion sort on it, and then recurse back up because it's, in practice, more efficient. But we are interested in the theoretical constructs here because it helps us understand the problem and the solution better. So at the very bottom, it's n nodes, n divided by there being n nodes, and that's t of 1. So it's constant work at that particular subproblem. At this level, or t of 1, whatever that the t ends up being, the recursive call is dealing with a single element of size 1. So it's not constant in that respect. It's actually going to be 1 times c, or 1 times n. So that's going to end up being n work. Now, if we ask for what k is n over 2 to the k equal to 1, okay? Because we might want to solve for k, even though we've got n over n here, it's n over 2 to the k. And we want to know what do we get at that bottom level? Like, what is the k? How many levels are there? So if you multiply both sides by 2 to the k to eliminate it from the denominator on the left, you end up with what? So the n goes down and then the 1 goes down. We just swapped them here. So you end up with 2k equals n, or n equals 2k. And to find out k by itself, in order to cancel out this exponentiation, we have to use logarithms. Okay, so you end up with k equals log base 2 of n. So k is the number of levels in the tree, and it's log base 2 of the number of nodes, right? So we found that each level does cn work. So in total, the work is c times n, and then there are k levels total. So c times n times k if our k is equal to log 2 of n. Remember, again, c is the constant amount of work done outside the recursive calls themselves per input element at a given level. But what's k again? It is log base 2 of n. So the total work is what? C times n times k. You end up with n log n. In asymptotic terms, the c constant factor is ignored, right? So it could be cn log base 2 of n, but we ignore that. So we would say that our t of n for this particular algorithm, whatever it may be, which is represented by the time complexity function 2t of n over 2 plus cn, we know that that's an element of n log n. So it's big theta, it's big O, it's big theta, also our n log n. Okay? Now the Master Theorem, this is another approach. So in addition to the recursion trees, we've also got, recurrence trees, we've also got the Master Theorem. The Master Theorem is a special technique for solving recurrences with a special form. So if you have one of this form, like we saw earlier, you've got A being number of subproblems as long as it's greater than or equal to 1, times t of the n over b, with b being at least 2 or greater than 1. We assume integers. The reason the b has to be greater than 1 is because we have to be shrinking, or this is not going to work with the Master's theorem. If it's the same size, like it's equal to 1, then it's definitely not going to work. And the f of n, of course, is the cost of dividing and combining. Anything that's not recursive falls under the f of n. Now, the Master Theorem has 3 different cases. These 3 different cases are as follows. So they're in this table here. Case 1 says that what you're doing basically is you are comparing the f of n. We'll look at these in detail in a moment, but you're comparing f of n, which is the non-recursive part, to different asymptotic boundaries that involve the recursive part, basically. Now, the way they do this is they use something called the watershed function, okay, which is n to the power log base b of a. Now, that is a special one, a special function that actually shows up in various contexts all over the place that math is used, especially when we involve recursion. So basically, you're taking the values that you obtain from the format of the recurrence relation right here, and you compare that f of n part at the tail end here with the stuff that you get from the a and the b and the the f of n with the a and the b. And this is what this does is this gives you an idea relatively of which one dominates. In other words, does the non-recursive work dominate, or does the recursive work dominate? And then that can tell you what the actual big theta or what have you is. Now, the reason it works is because if you have f of n in the big O, if it's big O of the n to the power log base b of a minus some small amount epsilon, we'll talk about that in a moment. If it's that, as long as if we made it equal to the watershed function, then it would be the middle case. But as long as it's explicitly and clearly below, okay, or bounded on top by this watershed function minus some small amount, then we know that it's case 1. And then the result ends up being this. This would be how we plug in the values again, and it's actually the big theta of the watershed function. So that means the recursive work dominates. And because the recursive work dominates, that's why we're using this watershed portion. For the equal contribution, meaning, so let's say we have linear contribution for both, you have end up with something n plus something n, they would basically, you would consider the one and then times the other. Okay, so for this one, you're comparing it directly to the watershed function. So if it falls into theta, meaning on average, if it is bounded tightly on both sides by the watershed function, then we give the result, meaning the actual t of n belongs to big theta of, and then you give this particular value. So it's basically the watershed function times log of n. Okay, this is how we end up with things like n log n. Right? And then over here, you have a lower bound. This is case 3. If you see that your f of n specifically has as its lower bound the watershed function plus some small amount to make sure that it's below. So basically, if this watershed function, which again represents the recursive part, if that part is contributing less than our f of n past an n greater than n naught at some point, that means that we know that the recursive part, because it's big omega, the recursive part is our bottom boundary, meaning that the recursive work is less than our f of n. So this means that the divide and combine work dominates. So in this case, we would just say that t of n is an element of f of n. And this makes sense if you think about it, because let's say we have these two terms, this plus this. If this side ends up being n, and then this side ends up being n squared, what's the big theta going to be? It's not going to be n, so we ignore the lower terms. So we say it's n squared. So it's the same thing here. If this part, the recursive part, ends up being n squared, and the non-recursive work is something like n or constant or something, we eliminate that. And we only consider the recursive part. That's why we have it here. Okay, we ignore the f of n on this one, and then we ignore the watershed function on this one. And then we use both if they both make equal contributions. Okay, so let's go a little further. I've got these again, just the format and the table again. So it means informally, you can figure out which case to choose by comparing the f of n component of the t of n recursion. And roughly speaking, after you plug in the a and b into this watershed function, the n to the power log base b of a, if our f of n falls under it, then we use case 1. If it's equal to it, we use case 2. And if it's greater than it, we use case 3. Now, this is kind of an informal definition because we're not really talking about that. What's that epsilon for in the actual condition we're doing the comparison for? Okay, so what does the formal definition mean more precisely? Remember that big O and big omega allow for the f of n to be equal to the g of n, okay? Which we are interested in, and that's the watershed function, n to the power log base b of a. But the Master Theorem needs more precision, okay? So if I say f of n is a member, and I eliminated this epsilon on both of these, then it would be very difficult to distinguish between these three, and we could not guarantee that f of n fell under this one. So the Master Theorem needs us to have f of n to be strictly less than the watershed function in case 1, or equal to it in case 2, or strictly greater than it in case 3. We can't leave it up to chance. So that's where that little epsilon thing comes in. It means a very small amount of change. And that's how we ensure that f of n is strictly smaller or greater, not equal, to the watershed function for cases 1 and 3 by use of that epsilon. But how does that affect powers in asymptotic orders? I'm glad you asked. So the next slide has the answer. So let's say that the log base b of a, that's that power of the watershed function, ends up being 2. And let's just set the epsilon to a very small amount, say 0.1. Okay, it's kind of an arbitrary amount. We just want it to be kind of small so we can see what the difference is. And let's see how n squared, which is if you just use the watershed directly, that n to that power, n to the power 2, compares to if you reduce it by this amount or increase it by this amount, that 0.1, okay, or 0.01. That's supposed to be 0.01, isn't it? Sorry, that was off. So let's see what happens. So you've got n to the power 1.99. You'll notice that even for size 10, we can start seeing difference. So the n to the power 1.99, which is an epsilon less than n squared, it's only 97. Okay, and for an epsilon greater than n squared, it is 106. But as this gets bigger, like up to 1,000,000, you can see it's pretty substantial, right? The difference is quite substantial. So basically this little extra that we're getting, so the 6 over here and the 3 here, and then you have, a couple hundred here, and then like 627 here, 72,000 here, and like 45,008 over here. You're increasing a gap. So you're increasing the gap, providing a gap, so that we know for sure our f of n is less than that thing. Now, by saying it's big O, remember what big O means? Big O means that provides an upper bound. So if our big O provides an upper bound, and I have the watershed minus epsilon, so that would be this column, for example, if we're dealing with 2, what does it mean for if I have a function that's bounded on top by this thing? What does that mean when we compare it to the actual watershed function? It means it's definitely bounded on top by the watershed function. Because remember, big O allows them to be equal. So maybe the particular growth rate of whatever our f of n is exactly 1.99. Maybe it's exactly the same. But that's not good enough. That's not good enough if we're comparing it to n squared and we need it to be exactly a little bit less or a little bit greater. So we're comparing it to this little bit difference. So we end up with the 1.99, and we can tell that there's a little extra gap here. So we know it's under it. So if it's under the 1 minus epsilon, it's definitely under the 1 without. And then for the big omega, remember this is a lower bound, not an upper bound, then if our f of n is always higher past a certain point than the watershed plus some little amount, then it's definitely higher than the actual watershed itself. For example, if our f of n at given points at 10 is higher than 106, so maybe it has 108 steps, it's definitely higher than the actual watershed function, which is 100. Okay, so the difference is substantial as n gets bigger as well. So that little tiny gap helps us to ensure the strictness of a less than or greater than, so that we know it's not equal to. So the equal to is its own special case. Okay, so, and I just explained these, so I'm not going to belabor that, but this is summarizing it in text for you. All right, so what does the Master Theorem tell us? So we compare the following parts, a times t times the n over b, by extracting a and b and filling in the watershed function to represent the work done by the recursive parts. Okay, so that gives us the work done by the recursive parts. And f of n is to represent work done by the non-recursive parts. This, I don't know why there's an s and an n there. That was weird. Okay, using the Master Theorem, we know which part dominates. And that helps us to determine the result, the theta, which is over here. This is what we actually want, is not just the f of n part, because that's what we were comparing here. We want to know this full t of n, since it could have recursive parts, or it has recursive parts. How do we know what its overall time complexity, what order it falls into? So what big theta? All right, so we figure out if the recursive or non-recursive is the lower term, and then we can eliminate that, like I said earlier. So if you find out that the f of n is dominated by the recursive work, then we say that the t of n is an element of the order of the recursive work. So that one's going to be higher, right? So again, the n squared versus n type thing. If f of n is n, and we have n squared is what the recursive work is, then obviously we don't even need the n anymore, right? That would be the same situation if we had a regular old non-recursive t of n that we were trying to find the big O of, right? We ignore non-dominant terms. Okay, so f of n, or for case 2, both are equally contributing, so you include both, as I said earlier, and then for case 3, the non-recursive part dominates. Okay, so since the non-recursive part dominates, this would be the scenario where f of n is, say, n cubed, and then the recursive part was maybe just n squared. So the n cubed dominates that, so we are more interested in that, and that's the category we put this in, big theta of n cubed in that case. All right, here's some examples. All right, let's take a look at example 1. So example 1, you are given this recurrence relation. It's 2 times t of n over 2 plus n. Okay, so we identify the different parts, a, b, and f of n. So the f of n is the kind of the straggler over here that has nothing to do with the recursion, right? So plus n. That's n itself. And we have 2 and 2. Okay, so how many subproblems each recursive call and the size of each subproblem. So is the divisor. So you have A is 2, B is 2, f of n is n. So we're going to compute the watershed function. That's our second major step. N to the power log b of A. So we end up with n to the log base 2 of 2, because both of these are 2. And we get n to the power 1. And that's just n. Okay, now, so that's the result of the watershed. Now, since we have the watershed, we can compare f of n to n. Since f of n is n, and that equals the watershed result n, we should choose case 2. So the result is that t of n is this case right here, so n to the log base 2 of a times log of n. That tells us that it's log, or n to the power, and that, oh, this is actually wrong. This should be n log n. There we go. So it's n to the power, the watershed function itself is just n to the power 1, which is n. So that's where that n comes from. And then because it's case 2, you always multiply it by log n, which is why we are putting the log n on the n here. So it's n log n. That's the answer. Example 2. All right, so now we have 3. For each recursive call, you have 3 subproblems, each of size half of the original subproblem. So 3t of the n over 2 plus, and then the extra work is n log of n. So you identify the values we need. The a is 3. That's the coefficient of the t of n. The b is 2, and then the f of n is n log n. We need to compute the watershed function. So to do that, we end up with n log base b, which is 2, of 3. What's the a value? So n to the power log base 2 of 3 is approximately n to the 1.58496. So next slide, what do? We compare that f of n to the watershed, or the f of n to the watershed function. Let's say that the watershed function is approximately 1.58, just to make our lives easier, and that's totally okay to do. We can truncate the 496, since strictly speaking, the 1.58 is lower than n to the 1.58496. So this further contributes to the gap that will be there when we add the 3, or add the epsilon. Okay, so our watershed is the 1.58496, and our f of n is n log n. You can pick any epsilon, so really anything below 0.58496, because we want there to be a gap, right? Because we've got n to the power 1, and then n to the power 1.58496. So we have to compare them. So let's reduce that gap by the 0.08. So that brings us down to even further, okay? Further away from the actual watershed value. So it's n to the power 1.5. Now, f of n is big O of n to the 1.5, okay? Because our f of n is the n log n, and that is definitely lower than, it's bounded on top by n to the 1.5. So that tells us we choose case 1. Since it's case 1, we will use this result. So that means that the recursive stuff dominates. Okay, so t of n is big theta of n log base b of a, which is n log base 2 of 3. That's our watershed. We actually calculated that earlier. So that's approximately n to the power 1.58. That is the category you put it in. What about this one? Similar to our first problem, but this one has additional work of n squared. Okay, so we identify the values we need. A is 2, B is 2, f of n is n squared. So we've got the a, the b, and then the f of n, which is the n squared. Compute the watershed function. You end up with n to the power of log base 2 of 2. That's n to the 1, and that's n. Okay, so our watershed is n. Our f of n is n squared. Okay, so clearly our f of n is going to be this third case. Okay, so that means we say t of n is big theta of f of n. And since our f of n is n squared, we use that. Okay. All right, now let's do some specific divide and conquer algorithms. Binary search is our first one on the docket. So let's look at that. The concept is we have an input of a sorted array, so it has to be sorted in order for binary search to work. We know that. If we have a sorted array of n of size n, we want to find a target x. The process is compare the target with the middle element. If they're equal, you're done. If the target is smaller than the middle element, then search the left half, and if the target's larger, then search the right. Each step cuts the array in half logically, or approximately half, and the time complexity we know is big O of log of n. Okay, so here's visualization. So if I'm searching, for example, for 13, here's my original array. I know the low, the mid, and the high. We'll look at code in a moment, but we know the low, the high, and then the midpoint. We find the midpoint, and that is 14. Okay, it's 14. Since the value we're looking for, 13, is less than 14, we search the lower half. So this is the next step. We can essentially pretend that the upper half doesn't even exist. So everything including the midpoint all the way up doesn't even exist. We find the midpoint recursively of this new part of the array that we're focused in on. There's 3 elements, so the one in the middle is our 12 here. And since 13, the target, is greater than 12, we search the upper half. Oops. We search the upper half. So then what you do, you can eliminate, you already had the 14, 18, 20, 25, 27 eliminated. You can eliminate the midpoint and anything lower, which is the 10, out of the picture, and then look and only search the what's left. The only thing that's left is the high, the mid, and the low, which is one single element, and that's 13. It happens to be in here. If it wasn't, then we would say, oh, didn't find it, rather. But it is 13. So we did find it, and it's at index 2. This is just recursive code, kind of a pseudocode thing. If the low is greater than the high, that means it wasn't found. Mid is calculated as the quantity low plus high divided by 2. Okay, and generally truncated down. If the mid is equal to the x, that means we found our target. So we return the midpoint, indicating that index is where we found it. Otherwise, if x is our target, is less than the midpoint, we recursively search the lower half. So low up to the midpoint minus 1. Okay, that's what we ended up over here when we did this part, right? So we ended up, or I'm sorry, this part at the beginning, right? We eliminated the upper half. We set the low still low, but then our upper part is then becomes the midpoint minus 1, which is at 2, which is why we ended up at that point. Otherwise, what it means is that if it's not equal and it's not less than, it has to be greater than. So we call binary search on A and X, so the array and the target, and then we have the midpoint plus 1, and then up to the high point. So the new low is what the old recursive calls midpoint plus 1 is, and then the high stays the same. Whereas this one, the low stayed the same, and then its quote-unquote high actually changed to mid minus 1. All right, here's some code, just for you to have for your reference. This is the C++ code on this side, and the Python code on this side, recursive code. All right, the binary search recurrence relation looks like this. So each recursive call halves the problem size. The cost model is that we have constant time per work call, or work rather, per call. The subproblems are of size n over 2 because we are dividing the workspace approximately in half each time. Okay, give or take 1. So that means the recurrence is t of n over 2 plus big O of 1. Now, the big O of 1 here at the end, it might kind of throw you off a little bit. You're like, wait a minute, how does f of n equal a big O of 1? What does that mean? We're saying that it's some amount of constant work depending on the application, okay, or the implementation. So we could just use some specific constant, like a 1, a 3, or a 5, or a 2, or a 7, or 17, or whatever you'd like. But ultimately, the constant won't grow, and t of n over 2 will. Okay? So how do we calculate this? We say that the a is 1, so it's implicitly in front of this t of n over 2, and then the thing we're dividing by is 2, so that's our b. We have 1, 2, and then f of n is big O of 1. We're going to compare our f of n, a constant, some sort of constant, because remember, we're interested in the growth rate, not a specific value. So if the constant's 160, it doesn't really matter if we find the other thing is growing. We're interested in the asymptotic relationships. Remember, let's not lose sight of the forest for the trees here. What we're doing here is finding finding where the time complexity function lives in terms of asymptotic complexity. So what order is it? What class does it fall under? Okay, what category is it in? What set is it in? So we know that any constant versus this watershed function, the watershed is going to be log base 2 of 1 because of the a and the b values. That's n to the power 0, okay, because log base 2 of 1 is 0, and that just gives us 1. So we have big O of 1 versus 1. Both are constant growth rates. Okay, remember, we're interested in the rates, not the specific value. So I've got a straight up 1 right here, and it doesn't matter if big O of 1 is 165. If we compare their growth rates, okay, right, you take the derivative, okay, since you guys love calculus, you take the derivative, that growth rate's the same because they're both constant. There's no growth. So that means they are the same. So we pick case 2. So T of n is big theta of the watershed times log n. And since the watershed itself ended up being 1, strictly, times log n, because that's the result for case 2. You have to include that multiplying by log n. You have a constant, 1 times log n, so that ends up just being big theta of log n, which is what we know the binary search to be. What about merge sort? Okay, merge sort is up next. All right, so the concept is that we have an input of array S of size n, and the process is divide, conquer, and combine. So you divide by splitting the array, the set, into 2 halves, sizes, well, it's going to be the size floor of n over 2 and ceiling of n over 2, which if it ends up even, it's going to be the same. So you typically end up either same or they might be off by 1. Conquer means recursively sort each half by calling merge sort, and then combine, merge the 2 sorted halves into a fully sorted array. Sorting is done after reaching arrays of size 1. This is the pure merge sort technique, and again, I mentioned earlier, in practice, like Java has an array, I think it's arrays.sort is the specific, there's a couple different sorting algorithms they use, but I think that one uses merge sort. What it does, though, is it goes down to about, in practice, they discovered arrays, when it gets down to size 7 after keep splitting. So if I have a size, 100 or whatever, it'll go to 50, then 25. It'll use merge sort on those. Then, about 14 or 12 rather, and then 6. When it gets to the 6, it'll just flat out call insertion sort. So it won't go down all the way to the size 1, because the overhead of continuing to go down all the way to size 1 is actually higher than just calling insertion sort on a constant number of cells, a very small number of items to sort it real quick, because the overhead is higher. All right, so the key property is that we always split evenly. Okay, it's evenly, or we would say approximately evenly. It has a predictable big O of n log n. Okay, so no matter how they are arranged, best case, worst case, what have you, we end up with a predictable big O of n log n. So here's the visualization of merge sort. Let's say I have these cells and I want to ultimately sort them. 38, 27, 43, 3, 9, 82, and 10. Okay, so there's 7 items here, so it's not even. So you're going to end up with 1 half. In this case, let's say we split it. This one could have ended up going to the other side depending on the implementation. But you've got 38, 27, 43, and 3. And then on the other side, this is calling merge sort on the halves. This is the split process. 9, 82, and 10. Then you split again, 38 and 27, 43 and 3. So this is split into 2. Then you have 9 and 82, and then the 10 is kind of a straggler. It just becomes its own thing. Since it's down to 1 cell in that one, it stays that 1 cell. So you end up down 1 more level. And then these, they technically do another split and then come together, but I'm visualizing it here like they're just kind of swapping. But these would go down to size 1 and then swap. So 27, 38, 3, 43. You would agree within these individual subarrays, they are in order. 3, 43, 9, 82, and 10. The merge process looks like this. You literally, for these two, for example, I would pretend like I have a little arrow pointing to this index over here, it's index 0, and then this one, the subarray's index quote-unquote 0, this first element. I'd compare 27 and 3. I find that 3 is smaller, so 3 goes to the first spot, and then I move over my little pointer or index that I have pointing to this this cell, and then I continue to compare because we haven't plopped 27 down yet, so I can't just keep going. I have to do something with 27 eventually, so I compare 27 to 43 and find out that it is less, so I empty that one up. Then the little index over here goes to 1. So now I have these two cells, 38 and 43. So the cell containing 38 compared to the 43, we find that 38 is less. So that means that this one is completely emptied. So whatever was remaining over here would get emptied into it as well. And the same thing, basic process goes over here. 9 compared to 10, 9 goes. 82 compared to 10, 10 goes. And then whatever's left because this one's already been emptied. So since this is in order, even if it had 3 or 4 more items over here, we would empty the rest of them out because there's nothing to compare them to. And they'd be in order. So we would assume that 82 is higher than whatever else would be remaining. All right, so you can agree that once we did our little merge here, 3, 27, 38, 43, and then 9, 10, and 82, each of these independently are sorted. So we shuffle them back in. The shuffling process is relatively cheap compared to doing like an insertion sort or something. So that's where we get a huge advantage with this. Okay, so we put the 3 down, put the 9 down, put the 10 down, put the 27 down, put the 38 down, put the 43 down, then put the 82 down. Then, since we're at the top recursive call, we have merged them all back into their appropriate slots, and it is where it's supposed to be. So it's sorted. All right, some pseudocode here. I'll let you look at that on your own. And then I also have, for your consideration, we've got the Python and C++ versions right here. So you can look at both of those. Okay. What's the recurrence relation for merge sort? Well, each recursive call splits the array into 2 halves of size n over 2. So there's 2 halves, there's 2 of them, and each of them are size n over 2. So our a and our b end up being a 2 and a 2. And then the f of n is an n. Okay, so that's what we're going to see with the Master Theorem. So the base case, we would assume that the simplest thing is that if we get down to that size 1 cells, they all do exactly, constant effort to be sorted because they're already sorted by definition. A single cell array, if it's got 1 element in it, that's it. Hey, I've got the element 5. Am I sorted? Yes, trivially so. So the height of the recursion tree is log base 2 of n, and there's n work per level because I've got to sum all the merges at that level, basically. It's a sum of the... Now remember, we're not counting the values at the cells, we're counting the amount of work, okay? So ultimately it has to do n merges, which is what we saw up here. Even though we did them in the order they needed to be done, and it kind of flops back and forth a little bit, it's still 1, 2, 3, 4, 5, 6, 7, 8 out of 8. So it did... all n cells got something done to them, and it was linear work. So that's why down here, we have the sum of merges being n at that level. So here's our Master Theorem. Because it is in this form, we've got an a times the shrinking value here plus some amount of work that's not recursive. We can use the Master Theorem. A equals 2, b equals 2, f of n equals this amount right here. This just kind of straggling by itself. So that's an n. And then we compare the f of n to the watershed function, n to the power log base b of a. And the f of n is n, right? From earlier, we found that out, versus our log base b, which is 2, of a, which is also 2. So log base 2 of 2. And we saw that earlier, that's n to the power 1 or 1. These are both n. So since they're both exactly the same, which one do we use? We use this one. Okay, so this ends up being the solution, the result. So we have it being t of n is big theta of the watershed function times log of n. What was our watershed function? What did we calculate that to be? The calculation of the watershed function is n, right? So it's n times, and then it's required that we have log n because it's case 2. So n log n. And that's what you know merge sort to be. Next up, we've got Quicksort. This is another advanced sorting algorithm. We're really kind of diving deep on these. Hopefully in a previous exploration of data structures and algorithms, you did look at some of these and they might be familiar, but we're diving a little bit deeper. We're applying theorems that you may have been told, hey, this is the, this is the asymptotic complexity, but maybe didn't cover how did you get it. Or you might have had an intuitive notion or done a recursion tree or something similar, but didn't do the Master's theorem. Or the Master theorem. So Quicksort looks like this. Array S of size n. So it's another array. We're trying to sort it. We want to divide. We choose, this is different than merge sort. We choose a pivot element and partition the array so that all the elements less than the pivot go to the left subarray, and all the elements greater than or equal to the pivot go to the right. Conquer is recursively sort the left and right subarrays by calling Quicksort. Combine is concatenate left and pivot and right. And there's no extra merge step. Merge step. The keynotes, though, are that the pivot selection strategy affects performance tremendously. So in best case, balanced partitions, it's big O of n log n, just like merge sort. In practice, Quicksort tends to perform better than merge sort if the pivot is correctly picked. But if you need guaranteed n log n, merge sort is your guy. Okay, that's the one you need. Because the worst case for Quicksort is actually big O of n squared. Big O of n squared. Why is it big O of n squared? That's like a quadratic sorting algorithm. How would it do that? Well, if you remember how Quicksort works, which we will look at in a minute, if the array is already sorted, okay, either ascending or descending, if it's already sorted, then when we keep picking the pivot, if you pick a bad pivot, let's say we always pick the first element, if you keep picking the first element, it's going to have everything to the right of it, nothing to the left of it. Then it goes on to the next one. Everything to the right of it, nothing to the left of it except the previous pivot. Then everything to the right of it, nothing left of it. So it's going to actually degrade essentially into insertion sort. Okay, so we want to try to avoid that. So picking a pivot is actually useful. Picking a good pivot. So picking one randomly is not terribly bad, but picking the first or last, you cannot guarantee performance. Okay, so the pivot choice determines partition balance. Balanced partitions lead to big O of n log n. Poor pivot choice leads to the n squared. Common pivot selection strategies are first element, last element. Those are bad usually. Random is a little bit better. Median of 3 is the one that's most common. Okay, you might think, well, why can't we just go through the whole thing and find the median of the whole list? Because that's another linear amount of work you're adding on for every call. Okay, so you're basically making it worse than as bad as a quadratic guaranteed, because you're gonna keep putting that extra n amount of work for every call. So median of 3 is constant time, because we look at the first element, the last element, the middle element, and then pick the median of 3 elements. The median of 3 elements, so it doesn't matter if the array is size 10 or size 100,000, the median of 3 elements is going to be the same. You're picking the median out of 3 elements, so it's a constant amount of work. So it's a good technique to at least reduce the chances, although it's still possible. It reduces the chances of getting worst case scenarios throughout the entire performance. Median of 3, constant time, gives a guarantee that you're at least not picking the worst value. It could be the second to worst value, possibly, or something, but on average tends to perform quite well. So let's say we have an array containing, this is just finding the median of 3. We're not yet doing anything with the actual full example. But median of 3, if I have this array and I just want the median of 3, I would look at the element in the front. That's a 9. That's first. There's a 6 in the middle, and then there's a 5 at the end. We go by the indices, obviously. So you have 9, 6, and 5. If I were to look at those and ask which one's the median value, it's the 6. So that becomes our new pivot point. That's our pivot point. We would place elements on one side or the other based on that pivot point. Now, in implementation, this one throws students off a lot. Usually you swap the median of 3 pivot into the last position or first position before calling the partition routine. It adds a tiny constant time overhead for much better average performance. Okay, so let's say we have our original, okay, this actually ends up being different colors than the subsequent slides, but it's the same array. This is just our basic introduction. 3 numbers at first. So we're going real slow on this first slide, and then we'll raise it up a little bit. So we want to find the median of 3. So I have an 81 in the first spot, a 17 in the middle, and a 15 at the last. If we look at these, we have an 81, a 17, and a 15. So our pivot actually ends up being the 17. It happens to be also in the middle of the array, but that's not always the case. So we swap that with the element at the front, or you could do the end, but we'll do the front. We'll put 17 at the front, put the 81, swap that into index 6. The next slide, you will notice that we will have two different little counters we're going to use to track where we are looking in our quicksort, in the recursion of the grand scheme of things. So we assign I, a purple arrow, which we will see over here, to track element 1, and J, which is an orange arrow, right, to track the last element initially. You will swap elements as you move I and J. You're going to come in from both sides depending. When I and J cross, no swap is performed, and the pivot is swapped with the element pointed to by J. And then that formally puts everything where it's supposed to be for that round. Okay? Now, let's... and then Quicksort's called recursively on the halves. Because the first time you go through, it's not guaranteeing that it's going to be fully sorted, but it will guarantee that everything on the pivot in the center, it'll say everything to its that's lower than it, everything to its left is going to be smaller. So smaller to the left of me, greater to the right of me. Right? That's song, maybe? No. Okay. So you're guaranteeing that. And then when you go down to the lowest, smallest numbers, we're actually going to end up sorting each one recursively. So right here, I moves to the right and skips over elements smaller than the pivot. So that's what it's doing. J moves to the left and skips over elements larger than the pivot. So that's what it's doing. So it's starting here. We know that the pivot is 17. So J, okay, if it finds one larger than the pivot, it skips over it. Okay. When they both stop, we swap the elements. If I and J cross, no swaps are made, and then we perform the pivot at with the element at J. Okay, so we've got this. We've got the 94 and the 15. The 15 or the 94. Okay, it skipped over the 17 because smaller than our. The 94 is greater than the 17. Okay, so we just keep I at that 94, so it doesn't move anymore. And then the orange arrow is at 15. This is our J value. It's at this cell 15, and the 15 is not larger, okay, than the pivot. So we keep it, our pivot 17, remember. So we just keep them both here. Now what do? We swap the 15 and the 94. The 94 goes to this side, the 15 goes to that side. Then what do? Okay. So then we can keep going. The 75 is the next element. That is larger than the pivot, so it skips over it. Okay, and then this one, the 11, smaller than the pivot, so it skips over that, right? So this one increments again to 96. 96 is not smaller than the pivot, so we stop at 96. The 41 is definitely larger than the pivot, so we keep going. 58 is also larger than the pivot, so we keep going. 28 is larger than the pivot, so we keep going. 95 is definitely larger than the pivot, so we keep going. 81 is larger than the pivot, so we keep going. Notice that all this time this I didn't change because the 96, remember with the I rule, it skips over the elements with smaller pivot and then stops when it finds one that is not smaller than the pivot. It did find one not smaller than the pivot. That's the 96. So it's stuck there until J gets to either crosses it or gets to something that it needs to swap. Okay, so we get the 35. That's definitely greater than 17. Now it finds a 12. Yay! So we stop. We found something smaller than our pivot of 17. Now what do? We swap those two elements. We swap the 12 with the 96. And at this point, you'll note that the J has moved to the right. Okay, and then the I moved to the left, and that we have swapped them. The purple arrow and the orange arrow crossed over. Okay, the orange arrow is the J value, and your next move, since they've swapped, is to swap the pivot, which was at the first cell, with the J value. Okay, so with what the arrow is pointing to, that it just crossed over. So 12, okay, and 17 are swapped. So you notice here, 17 is our pivot. Everything to its left is smaller than it. And if you look to everything to its right, even though they're not sorted yet fully, they are greater than it. So we could argue that 17's in the right spot, right? Everything else less than it is closer to where it should be. Now, then you do a second pass. So the second pass, 17 is kind of its, anything less than it, we are sorting on that. Anything greater than it, we are sorting on that. And you perform the quicksort recursively. Okay, so recursively sort that. You end up with, there's two sets of purple and orange arrows, right? So the 12, the pivot is the pivot 12 ends up being the pivot. It's already in the first spot, so we leave it. Now over here, what do we have the pivot as? The pivot would be, let's see, 96, 28, or 94. The middle is the 94. So you end up with 94 being the pivot on this side, and then the 12 being the pivot on this side, right? So I know there's a lot going on, so you might have to kind of slow this down, rewatch this portion of the lecture a couple times if you are having trouble understanding it, and go through the slides a few times. So 12, 15, 11. 12 is the pivot. 15 is greater than it. It has not found anything smaller than it, so it keeps going. And then over on this side, the 94 is the pivot. So it finds 94 is the pivot. So 35's less than it, so we skip it. 81's less than it, we skip it. 95 is not, so it will end up stopping there. But let's look on this side for a second. Okay, so 12, 11, and 15, they crossed over. So that means the 12 and the 11 will be swapped. So we have 11, 12, 15. That ends up being sorted. Okay, on this side, we keep going. Let's say we called quicksort again and found out eventually we would recombine it and find out that this part is actually sorted now. 17 is in the right spot, and now this part needs sorted. So we keep going. 95 is greater, so that the I stops at 95, since 95 is greater than 94. Since J was already stopped, now we swap the I and the J, so the 95 and the 75. So it basically moves one to the side it's supposed to be on, and then the other to its side, putting it in the correct side of the barrier, which will end up being our pivot. And you keep going. You've got 28 and 41. 28 is smaller than the pivot. 41 is smaller than the pivot also. So that stays. 41 stays. 58 smaller. Keep going. 58 and 41. Since 58 is less than 94, I keeps moving. So they end up on the same one. Okay. 41 is less than 94, so the I keeps moving. Now, all this time, J is staying where it's supposed to be. Okay, it just stays at the 41. The I has now passed it. 95 is larger than the pivot. So now we have both of them stopped, so we swapped them. Okay. All right, so we swap the pivot with it, sorry. So we swap the pivot with the thing that the orange arrow or the J is pointing to. So the 94, which was the pivot, ends up going there, and then whatever was there ends up going at the front. Right? So you can see the stuff to its right is greater than it, stuff to its left is smaller than it, and we just keep going. Okay, I didn't complete the whole thing because I'm hoping that you'll do it as practice, okay? And at some point, any normal person will go insane trying to copy and paste that many little rectangles, or watch someone talking about little rectangles. So I would recommend kind of doing it on paper and getting used to the process, because it's very, very likely, wink, wink, that you'll end up with this on quizzes, tests, something like that, or projects or something. Okay, here's the pseudocode for quicksort. We take the array, have the line, the low and the high rather. If the low is, as long as the low is less than the high. Now, I know it's an if statement here, so it might throw you off a little bit, but since we have recursion involved, the if statement is kind of going to have, with the recursion, it's going to have a little bit of an iterative behavior here. So it will act kind of as a continuation statement, or the recursion continuation statement. So we call partition to find it, find the partition, or the pivot rather, and then quicksort is called on each of the halves, the lower half and then the upper half. Okay. Now this one's not good. This one is not actually median of 3. Okay, this particular implementation is not median of 3. This is looking like it's just doing the last element, okay? So keep that in mind. You might have to rewrite the partition if you want median of 3. Okay. What does the partition look like for this one? Yeah, it's doing the same thing. It's kind of partitioning to the ARR at high, which it should be the median of 3, but these are not. These are using the upper end or higher end. So what is the best and average case? So again, worst case is completely unbalanced. So the sum of the first integers, n integers, is n squared. But the best and the average case, each partition splits the array evenly, so each with size n over 2. Partition step takes big O of n time, so you end up with the t of n equals 2t of the n over 2 plus n. That's the same as merge sort, okay? What about the Master Theorem? So worst case doesn't fit the Master Theorem neatly, so we analyze it. We'd have to use other techniques to get the n squared. But for the best and average case, it does fit the Master Theorem, so we can apply that. So we've got A is 2, B is 2, f of n is n. Compare f of n to the watershed, so we're comparing n to the watershed, n to the power log b of n. N compared to n to the log base 2 of 2 is n to the power 1, and that's n also. So they're the same, so that means we pick what? We pick case 2. Case 2 comes up a lot. They all kind of do, but for the ones we're talking about, case 2 comes up a lot. So since they're the same, we find the result in applying the watershed multiplied by log of n. So what was our watershed result? It is n. N times log n is n log n, and that is our solution. And then this is just giving some trade-offs about the types of algorithms, best and average cases versus worst cases. Memory use. We didn't really talk much about space, so this is memory use. Quicksort tends to have less space usage. So it has log of n space versus big O of n space for merging. And stability, preserving the order of equal elements, merge sort does. Pivot split strategy, merge splits in half. Pivot choice is critical. Okay. Cache performance, ease of implementation, practical speed, etc. So you can look at those. Terminology before moving to a trade-off comparison between quicksort and merge sort. A couple terms should be understood first. So locality. There's two different kinds of locality that we generally talk about. Spatial locality, which is if you access one memory location, you're likely to access nearby locations soon. So an example would be scanning an array from start to finish. It's very likely if you scanned or went to the element at 0, you're probably going to go to 1 next if you're scanning. Hardware benefit, CPU loads chunks or cache lines from RAM, so sequential access hits the cache often. So we're really digging down into the hardware on that one, but spatial locality can be a very useful property. Temporal locality has to do with time. If you use a memory location, you're likely to use it again. Okay, so this one's not how are they relative to one another. It's that if you used it once, you'll probably use it again. Example would be a variable in a tight loop, repeatedly accessed. Hardware benefit would be data already in the cache stays useful. So your CPU and other devices have cache memory, which is very, very small amount of memory, but it keeps stuff that it uses often in there. So by different what we call caching algorithms, like least frequently used is a cache replacement algorithm, least recently used, and things like that. So it's when do we get stuff out of the cache and then keep stuff that we do use in the cache. At a very high level, Netflix and companies like that kind of do that. They have storage near different locations so that you can get your streaming services faster. And they have cache replacement policies in different areas. Say everyone's watching a specific show. Well, it's definitely going to keep that show in the repository so that everyone can access it without it having to make a request to, say, California or somewhere far, far away in order to pull the data in, right? So it'll keep it local. So in sorting, Quicksort tends to have an excellent spatial locality because partitioning works in place. Okay, meaning we don't need auxiliary memory. We just keep moving around and swapping stuff within. okay, within it, and often accesses consecutive elements. Merge sort can lose some locality because merging reads for multiple subarrays, potentially jumping around in memory, but still has decent sequential reads. External sorting is another term you should be familiar with. This is used when the data set is too large to fit in main memory, which is RAM. So it has to be stored on disk or another slower storage medium, what we would call secondary storage devices, during processing. Even a solid-state drive is slower than RAM. Okay? So an example might be sorting a 100 gigabyte file on a machine with only 8 gigabytes of RAM. You can't have the whole thing in memory. It's impossible. So your storage tends to have a whole lot more room than RAM. Okay, that's on the smaller side of RAM, but still, you've got your operating system and other stuff going, so you're probably using 4 or 6 gigs at most, probably less than that, probably 4, maybe 3 to 4. So you've got 100 gigabytes that you have to sort. I cannot do it all at once. So a general approach for external sorting would be something like break the data into chunks that do fit in memory that we can use, sort each chunk in memory, often with merge sort, write those sorted chunks back to disk, so they're in these little sorted pieces, almost kind of a meta merge sort, and then merge the sorted chunks into multiple passes until the entire data set is stored. Okay, Quicksort. I'm not sure why that ended up... I don't know that that's a different font, maybe? No, it's just not bold. Okay, so Quicksort is usually faster on average for large in-memory arrays. This is due to the in-place operations and good locality that we talked about, but it requires careful pivot selection to avoid worst case. Merge sort often offers guaranteed big O of n log n performance and stability, and that is preferred for linked chains, external sorting, that we just talked about, or when input size and distribution are unknown. All right, some exercises. If you can kind of copy or hold your hand up over the solution. I probably should have put them on separate slides. But the problem is search for 42 inside of the 5, 8, 17, 23, 42, 56, 74. It's a sorted array, and we want to perform binary search on it. So what would be the step? Step 1, middle is 23, so we go there. And since we are looking for 42, we know it's bigger than that, so we look in the right half. So what do? We look in the half 42, 56, 74. We find the middle of that, which is a 56, right? So what do? If we just looking at this, would we search the left or the right subarray? It would be the left because it's smaller than 56. And now the middle, okay, if you're calculating this, we end up with the left half being 42. There's only one cell now, so that better be it, or we can say, hey, we didn't find it. But the middle is 42, and that does actually happen to be what we were searching for. Okay, so in only just a couple steps or passes, we have solved it. Example 2, merge sort. This is a very simple one, just to keep it very, very easy. Sort the array 38, 27, 43, 3. Solution would be split into halves. So you get 38 and 27 on one side and 43 and 3 on the other side at the first level. Sort each half recursively. So we're pretending 38, 27 is our top level one. So we split that into 38 and 27. Those are single-sized arrays, quote unquote, so that we can just merge those. So we shuffle them into the right place. That ends up being 27, 38, which is sorted. And then the same thing over here, 43 and 3. We end up merging those into 3 and 43. And then we go back up from our recursive call. We have two sorted subarrays, 27, 38, and the array 3, 43. We compare 27 and 3, since those are the first elements of each. 3 goes first, so this side stays on the 27. This one goes to the 43. So we take the 3, that's the first element that goes into our solution. And then we have 27 versus 43, take the 27, so that one increments on this side, and the 43 stays on its side. So we put the 27 in the second place. 38 plus 43, 38, we take it, put that there, and then since this half subarray, this subarray over here, is done, then whatever's left, we would dump into the remainder of the array. In this case, it's only one element, but even if it was 10 elements, we would still dump it, okay, into the remainder of it, because we wouldn't have to do any more comparisons, right? because this one's done. All right, very good. Quicksort, 9376285. Pick I would generally give you instructions, but you can assume by default we pick the pivot via median of 3. So the median of 3, 9, a 6, and a 5. So 5, 6, and 9, if we were to organize those, in order, right? 5, 6, and 9. The 6 would be the median. So we pick that. That's the pivot. Partition it. So ultimately you end up with you would partition and then end up with the cells that are less than it on one side. This is obviously showing you a very, very condensed solution. I would, for your actual assignments, you would want to go step by step, okay? But this one's condensing it so you can see the solution more easily. But you end up with 3, 5, 2 on one side and 7, 8, 9 on the other. And then subarrays 3, 5, 2, 7, 8, 9. And you continue picking the new pivot and sorting recursively. So you end up with 3, 2, and 5. So 3 is the median. Put the 2 to the left of it, the 5 to the right. So you end up with 2, 3, 5 sorted. That ends up in the final solution. And then the 6 is our original pivot. And then you end up with 7, 8, 9. That ends up with 8 as a median, but it's already sorted. 7's to its left, 9's to its right. It's already sorted. Merge everything back together. You end up with 2, 3, 5, 6, 7, 8, 9. All right, now we're at the summary. So the core ideas are that we break a problem into smaller sub-problems of the same type. That's the core of divide and conquer strategy. Solve sub-problems recursively, combine their solutions to solve the original problem. Key characteristics are that the problems must be divisible into smaller instances of the original problem. Okay, so sorting is a perfect example. Sorting a size 100 versus sorting a 50, the actual general process is the same. So after we have the subproblems sorted independently and recursively, all the way down to whatever the base case is, we then combine the results, and the combining process should be efficient. Okay? Divide and conquer is one of the most powerful algorithm paradigms, and understanding it builds intuition for advanced algorithms, like Strassen's matrix multiplication that's used with a lot of GPU and even like AI stuff at certain levels. It's more efficient for certain sets of matrices than doing the matrix multiplication, kind of the general brute force technique, which is n cubed. Strassen's is less than that. They believe a matrix multiplication algorithm exists that is quadratic, so big O to the power 2. Whether it would be actually practical or not, we're not sure yet, but they do believe one exists. No one has ever found it yet. FF2, fast Fourier transform would be another one, and then others. We also learned about the Master Theorem, so this is just for reference for you to keep it easy. I put the general form here, has to be of some sort of form. An f of n in this case, don't get confused because the f of n here is not... it's going to, but not going to, fall into the definition of like a big O or big theta or big omega. You have to think of it as whatever is straggling that isn't recursive. Whatever's at the end here, the little straggler at the end here that is not recursive, that's what is represented by the f of n. Then you compare it to the things like the big O, big theta, big omega. And then you can find the result based on that. And algorithms. So we went over a couple different algorithms. We looked at binary search, which splits the search space in half each step. The time is big O of log n, so it's logarithmic. Space, we didn't really go into, but it's constant space iterative, or log of n if we use a recursive approach. Merge sort always splits evenly, and the merges themselves take big O of n. And it's log of n splits down, so it's n log n. But it does need big O of n extra space. For quicksort, partitions around a pivot in place, so we don't use extra space. Best average case is n log n, linear arithmetic, and worst case is quadratic without a good pivot choice. All right, so that's what I have for you for this particular set of topics for this video lecture, and I hope that was useful. Talk to you later. Bye-bye.